This tutorial is to simplify radicals using a prime factorization method that I like to call the PROM method. It's easy to remember, and students usually do very well with simplifying radicals by using this method. My objective is that you can take any integer and that's underneath the radical and that you can simplify it. I'm going to actually teach this by example, and then I'll let you practice a few. I'll give you the algorithm that I use, and then I'll explain to you why it works, and I'll show you why it might sometimes be necessary to simplify radicals. The first thing I want to know, though, is what does it mean that a radical is not even in simplest form? You can read what's on the left, so let me just start with the square root of 50. The reason the square root of 50 is not in simplest radical form is because there's a perfect square bigger than 1 that factors into 50. In this particular case, it's 25. So I can write the square root of 50 as the square root of 25 times 2, which I can then write as the square root of 25 times the square root of 2. But the square root of 25 is 5, and so the simplest radical form for the square root of 50 is 5 times the square root of 2. This method of finding the largest perfect square would work, but for some students that becomes kind of tricky to know the numbers and to know what factors in. So there is another method we can use, and I'm going to show you by example first. The first example I want to use is I want to simplify the square root of 60. Watch me this time and watch me on the second time, then I'll give you the algorithm, and then I'll let you practice some on your own. The way I'm going to simplify the square root of 60 is I'm going to break it down into its prime factors. You can do it many ways. I'm going to write 60 as 6 times 10. I'm going to write 6 as 2 times 3, and 10 as 2 times 5. If I write these prime factors from smallest to largest, my prime factorization will be 2, 2, 3, and 5. Let's say I decided to try 60 a different way. Instead of saying it was 6 times 10, maybe I thought of 60 as being 2 times 30. And then maybe I thought of 30 as being 5 times 6, and 6 as being 2 times 3. When I write these from smallest to largest, I get 2, 2, 3, and 5. Notice that no matter how I go about factoring 60, the prime factorization form is 2 times 2 times 3 times 5. So I've got this square root of 60, and I know its prime factors written from smallest to largest are 2, 2, 3, and 5. 2, 2, 3, and 5 are trying to decide whether or not they're going to go to the prom. Some may go to the prom, some may stay home. I'm going to draw a house. The house is actually a radical. The way that they decide whether or not they're going to go to the prom is they're going to see if they have a perfect mate. Well, 2 has a perfect mate. Because this 2 has a perfect mate, they fall in love, they become 1, and they go to the prom. 3 looks around, and 3, I used to use star-bellied sneetches because they have to have another exact match. 3 doesn't find an exact match. It's not going to take a chance on 5, and so 3 is going to decide to stay home. Same thing for 5. 5 doesn't have a perfect match. No big deal. 5 is also going to stay home. Now, whether you go to the prom or whether you stay home, you're always going to have a good time. So the 3 and the 5 are going to be timed together or multiplied together. My answer is going to be 2 times the square root of 15. I can simplify the square root of 60 as 2 times the square root of 15. One more example, then I'll give you the algorithm. How about the square root of 108? All right, we're going to take the square root of 108, try to break it into prime factors. I could do a lot of things, maybe 2 times 54. 54 is 6 times 9. 6 is 2 times 3, and 9 is 3 times 3. So the prime factorization of 108 is 2 times 2 times 3 times 3 times 3. Going to decide who goes to the prom and who doesn't. So I'll draw a house. 2 looks around for its perfect match. Wow, it found one. They become 1, and they go to the prom. 3 looks around for its perfect match. Ooh, it found one. We're only going in 2s. We're not going in 3s. These 2 become 1, and they go to the prom. This 3 here, I say something like tramp stole my man. I don't know, but 3 is all by itself now. No big deal. I'll stay home. Rather you go to the prom or rather you stay home, you always have a good time. So I'm going to multiply the 3 times 2, and the simplest radical form for the square root of 108 is 6 times the square root of 3. I wrote down the algorithm in case you need it. Here it is. We're going to factor the number, draw a radical sign, figure out which ones are going to the prom, which ones are staying home, multiply all the numbers together, and that's going to be my answer. If you want to pause the video and write this down, fine. I'm going to move on so the video doesn't last forever. Okay, try one on your own. I want you to pause the video and simplify the square root of 700. Hopefully this wasn't too hard. I've got the square root of 700. I can write that as 7 times 100, which is 10 times 10, which is 2 times 5, and 2 times 5. Writing these in form from lowest to greatest, I have 2 times 2 times 5 times 5 times 7. I'm going to draw my house. The 2's become 1 and go to the prom. The 5's become 1 and go to the prom. The 7 stays home. My answer is going to be 10 times the square root of 7. Problem 2. Pause the video and see if you can work this out. This was kind of like a trick question. If I want to simplify the square root of 15, 15 is 3 times 5. I've got them in order from smallest to largest. I draw my house. 3 doesn't find its perfect match. It stays home. 5 doesn't find a perfect match. It stays home. Doesn't matter. They still have a good time. My answer is the square root of 15. Oh, look, square root of 15 is already in simplest form. There is no perfect square bigger than 1 that actually divides into 15. One more. Pause the video and simplify the square root of 128. Here we go. The square root of 128. I can write 128 as 4 times 32. I can write 4 as 2 times 2. I can write 32 as 8 times 4, which is 4 times 2, and a 2 times 2. 4 is also 2 times 2. Holy cow, when I get through, I've got a bunch of 2's. In fact, if I add them up correctly, I think I have 7 of them. So I'm going to write my 7 2's. Draw the house. The first set of 2's become 1 and go to the prom. The second set of 2's become 1, go to the prom. The third set of 2's become 1 and go to the prom. This 2 stays by itself and stays home. Whether you go to the prom or whether you stay home, you always have a good time. 2 times 2 times 2 is 8. The simplest radical form of the square root of 128 is 8 times the square root of 2. All right, why does the prom method work? Well, let me go back to the square root of 50. I have this square root of 50, and I break it into its primes, 5 times 10, 2 times 5, writing it as 2 times 5 times 5. Notice what I've got. I'm grouping these things together, so I've got a 2 that stays here. I also have this 5 and this 5. Well, what's 5 times 5? It's 25. Because these two numbers are identical, when I multiply them together, I'm going to get a perfect squared. Well, what is this? This perfect square is 5 squared. If I take the square root of 5 squared, it's going to give me a 5 on the outside of the radical. That's why I'm grouping these things up as 2, and that's why I have to be really careful. Once we find the 2 that are in common, they have to become 1 to go outside the radical. And sure enough, my answer is 5 times the square root of 2. All I'm really doing when I'm taking these 2 that are together is I'm turning these things into perfect squares that can therefore go outside the radical. It's going to work every time. Why on earth do I bother to simplify radicals? Sometimes simplifying radicals helps us see patterns that we otherwise might not normally know. I have 3 isosceles right triangles, and I'm going to use the Pythagorean theorem to try to figure out what the hypotenuse is. Well, for this one, I'm going to say 2 squared plus 2 squared equals x squared. 2 squared is 4. This is 4. So x squared is 4. The length of the hypotenuse of this first right triangle is the square root of 8. The hypotenuse for a 3 by 3 isosceles right triangle, well, 3 squared is 9, and 3 squared is 9. 9 plus 9 is 18. So the hypotenuse must be the square root of 18. And over here, the hypotenuse must be the square root of 50. Well, that doesn't necessarily tell me a whole lot, but look what happens if I simplify these radicals. The square root of 8, if you go back and do what we did before, you'll find simplifies to 2 times the square root of 2. And the square root of 18 simplifies to 3 times the square root of 2. And the square root of 50 simplifies to 5 times the square root of 2. All of a sudden, we're able to see a pattern that we may not have noticed before. And that is, if I have an isosceles right triangle called a 45-45-90 triangle, and I know the length of a leg, the hypotenuse is always the length of that leg times the square root of 2. If I hadn't simplified my radicals, I don't think I might have ever seen that. There are other different ways that simplifying radicals helps you see patterns. And besides that, you may just be required to simplify a radical anyway, just to make us feel better about torturing you. Hopefully this has helped you, and hopefully you'll be able to use the PROM method to simplify any radical your teacher might give you. Talk to you later in a different video.